Let's talk about something that trips up a lot of students: equivalent resistance. You're staring at this complex circuit, and it just seems impossible. But trust me, it doesn't have to be. We're going to break down series and parallel circuits in a way that just clicks. Let's get right into it. You ever look at a circuit diagram and your brain just kind of fogs up? Yeah, you are definitely not alone. But our goal today is to swap that confusion for confidence. By the end of this, you'll have the tools you need to simplify these networks. No problem. Okay, so first things first. Before we can even talk about series and parallel circuits, we need to get a handle on the main idea we're chasing. What exactly is equivalent resistance? Well, it's pretty much what it sounds like. It's the value of one single imaginary resistor that you could swap in for a whole complicated mess of other resistors, and the circuit would behave in the exact same way. Our whole job is to find the value of that one magic resistor. And this picture shows the idea perfectly. We start with a circuit on the left that looks a little busy, right? It's got a few resistors. Our goal is to boil it all down to the super simple circuit on the right, with just one single resistor, our REQ. It makes analyzing the whole thing way easier. All right, let's jump into our first type of connection: resistors in series. Now, if you remember only one thing about series circuits, make it this: there's only one single path for the current to flow. That's the key. And you can see it right here. The resistors are connected end to end, kind of like links in a chain. Because there's no fork in the road, every bit of current has to go through R1 and then through R2, and so on. What does that mean? It means the current is exactly the same through every single resistor. And here's the best part about series circuits. The math, it's about as easy as it gets. To find the total equivalent resistance, you literally just add up all the individual resistances. R1 plus R2 plus R3. That's it. Let's see how that works. Imagine we have three resistors hooked up in series: a 3 ohm, a 4 ohm, and a 5 ohm. We just plug those numbers into our formula. Rs equals 3 plus 4 plus 5, which gives us a grand total of 12 ohms. Simple as that. So here's the big takeaway, the key rule. Every time you add another resistor in series, you're basically adding another obstacle for the current. You're making the path harder to travel, so the total resistance of the circuit will always go up. Okay, moving on to our second type: resistors in parallel. And if series circuits were all about a single path, you can probably guess what parallel circuits are all about. They're defined by having multiple paths. Here, the resistors are connected side by side. Think of it like a river that splits into several smaller streams. The current flows to a junction, and then it has to divide itself. Some of it goes down the path with R1, and the rest goes down the path with R2. And because they're connected like this, the voltage across each of these parallel branches is exactly the same. Now, don't let this formula scare you. It looks a little more intense, but stick with me. It's all about adding up the inverses, or reciprocals, of each resistance, and there's a cool reason why. The inverse of resistance is actually a measure of how easy it is for current to flow. So with parallel circuits, we're basically adding up all the easy pathways the current can take. Let's walk through an example. We have a 4 ohm and a 6 ohm resistor in parallel. We set it up. 1 over Rp equals 1 over 4 plus 1 over 6. We need a common denominator, right? Let's use 12. So that becomes 3 twelfths plus 2 twelfths, which gives us 5 twelfths. Now wait, this is the step everyone messes up. That's 1 over Rp. To get the final answer, you have to flip that fraction upside down. So Rp is actually 12 over 5, which equals 2.4 ohms. Don't forget to flip it. And here is the really interesting, kind of counterintuitive rule. It's the exact opposite of series circuits. When you add more resistors in parallel, you're opening up more lanes for the current to flow through. Think about it like opening more checkout counters at a grocery store. More paths mean less overall congestion, so the total equivalent resistance always goes down. Notice our answer, 2.4 ohms, is smaller than either of the resistors we started with. All right, you've learned the two fundamental combinations, so let's put it all together now. We'll create a little side-by-side comparison, your complete toolkit for solving any of these problems. And here it is, the whole story in one place. For series, think single path, the current is the same everywhere, and the total resistance just adds up and gets bigger. For parallel, think multiple paths. The voltage is the same across them all, you use that inverse formula, and the total resistance always gets smaller. These are the core rules that will get you through. Honestly, the best way to really get this stuff down is just to practice. Take these two rules, find some problems, and just work through them. The more you use these formulas, the more it all becomes second nature. And there you have it. You've now got the core tools to simplify any series and parallel circuit they can throw at you. I really hope this helped everything click into place. If it did, please consider liking and subscribing for more easy to understand explainers like this one. And hey, let me know in the comments what topic you'd like me to break down next. Thanks for watching, and I'll see you in the next one.